Hello everyone and welcome back. My name is Mr. Kovalt and in this video we're going to talk about baking chicken. Yes, that's right. We're going to learn about baking chicken and how the temperature is going to be related to the amount of time needed to bake the chicken, and we're going to figure out what the activation energy of such a baking process is, as well as what would be the number of minutes or the amount of time you would need to bake a chicken for 400 at 400 degrees Celsius, or sorry, Fahrenheit. Okay, let's get into this. So, here's the problem. While looking up recipes in a database, you find several different recipes for baking chicken. These recipes are all very similar: chicken parts, baking in a basting sauce, so on and so forth. The only significant difference is that each recipe specifies a different oven temperature and baking time. So here we have our data. This is the oven temperature at Fahrenheit. And then this is the baking temperature in minutes. So we see at 350 degrees Fahrenheit, it takes 90 minutes to bake the chicken. At 375, it takes 75 minutes to bake the chicken. At 500 degrees Fahrenheit, 30 minutes, and 300 degrees Fahrenheit, 135 minutes. So we're going to assume that the rate of the baking is proportional to the reciprocal of the time. So 1 over the time. So rate is going to be proportional to 1 over time. And so we'll take that in. We're going to take that in consideration. It says estimate the activation energy of the baking of the chicken under these conditions by graphing the data. Yes, we're going to graph the data. I'm going to show you my graph after I've graphed the data, but we need to set up our data. We need to set up the data so we can graph it, and I'm going to basically show you how to do that. And then the next question is, for how many minutes would you allow a similar recipe to bake if you use an oven temperature of 400 degrees Celsius? So, long story short, what we're going to do is we're going to have to set up our data, right? So our data table, the data in the data table, we're going to have to set that up so we can graph it. And then once we graph it, we're going to get an equation, and then we can use that equation to find how many minutes it would take at 400 degrees Fahrenheit. So let's go ahead and set up our data. So when we are going to graph our data for answering this question, we have to recognize that we have temperature versus time. And if we're taking the rate being proportional to the reciprocal of time, then what that means is that we can use the Arrhenius equation, or we can plot our data to get as a Arrhenius plot. And so if you remember, right, the Arrhenius plot is a plot of 1 over temperature on the x-axis and the natural log of the reaction, the rate constant for the reaction. And so in this case, since we are taking that the rate is proportional to the reciprocal of time, then we can find the rate constant is also going to be proportional to the reciprocal of time. So we can pretty much set that equal to the reciprocal of time and then take the natural log of that. And so what we're going to have to do also is we're going to have to take our temperature, which is in Fahrenheit, and we're going to have to convert that to Kelvin, because when we plot this, our temperature needs to be in Kelvin. So we need to take the data that we're given in the table and fix it so that way we can make this plot here. So let's go ahead and do that. So let's go ahead and do the temperature first. So what I'm going to do is I'm going to label these as points 1 through 4. And since this is the lowest temperature, I'm going to make this number 1. Then 350 is going to be point number 2, 3, and 4. So increasing temperature and decreasing time. So let's take the temperature. We're going to have to take our Fahrenheit temperature, so let's label those. So T1 is going to be equal to 300 degrees Fahrenheit. T2, bear with me, T2 is equal to 350 degrees Fahrenheit. T3 is equal to 375 degrees Fahrenheit, and T4 is equal to 500 degrees Fahrenheit. And so what we need to do is convert the Fahrenheit into into Kelvin. So maybe you know the formula that gives you directly there. There probably is one that you can probably put together. But typically you could do 2 steps. And so the formulas, I'll write them down here for just briefly. So to convert, we would need to convert Fahrenheit to Celsius. So that's going to be your degrees Fahrenheit minus 32. So there's your degrees Fahrenheit. And then we're going to multiply by 5/9. So this would be the equation. Let me double check that I got that right. I don't want to make any simple mistakes. Yes, that's correct. So this equation here is what you would use to convert your Fahrenheit to Celsius. And then to convert Celsius to Kelvin, you would just say Kelvin is equal to the degrees Celsius plus 273.15. So first you would convert using this equation to Celsius, and then you would convert your Celsius to Kelvin using this equation. So it's pretty straightforward. I'm going to skip all that so you don't have to bother with the calculations, but I would encourage you to do the calculations, follow my work, because I make mistakes sometimes. So if you find a calculation error, let me know. So first thing I want to do is convert this to Kelvin. I've done the calculations. So what I got was for T1, 422.039. So that goes to 422.039 Kelvin. When I calculated T2, I got the Kelvin 449.817, 449.817 Kelvin. Let me double check, 449, yes. And then for number 3, I got 463.706. 463.706 Kelvin. 463.706. Yep. And then for 500, I calculated, what did I calculate? 533.15. 533.15 Kelvin. Okay, now that I have the temperature in Kelvin, remember, I have to plot my data as 1 over the temperature, the reciprocal of the temperature. So I need 1 over the temperature. So I'm going to have to take the reciprocal of these. So when I take the reciprocal of these, or take 1 divided by these, so 1 divided by 422.039 is going to give me the reciprocal temperature. And so when I do that, let me see, I get 23,694. So this then becomes 0.00 23,694. 23,694, and that's per Kelvin, so 1 over Kelvin. So it's K to the -1. Let me make that more clear, like so. And then I do the same thing, 1 over 449.817, so the reciprocal, and I get 2.02223. Okay, so that's going to give me 0.0022223 per Kelvin. Let me double check that out. Okay, yep. And then for this one, I take the 1 over Kelvin or the reciprocal, and I get 0.0021565. 0.0021565 per Kelvin. And then for the last one, I get 0.0018756. 18756. 18756 per Kelvin. Okay, so now I have one set of data. So that's my temperature. Now it's 1 over temperature. So I'm done with the oven temperature. And now for the baking time, I have to find my rate constant. So for each temperature. Remember what it says. It says assume the rate is proportional to the reciprocal of the time, right, that it takes to bake the chicken. And since your rate constant is directly proportional to the rate, and we're saying that the rate is going to be, related to or proportional to the reciprocal of the time, so therefore we can say that the rate constant is going to be related to the reciprocal of the time. So let me erase this. So I'm going to put these points down here. So for number 1, we're going to say that K, the rate constant K1, is going to be equal to 1 over the number of minutes, 135. 135 minutes. And then if we calculate that, then that's going to be what I get. 0.007407. 7407. So 0.007407, and that's per minute, right? Because minutes on the bottom. And then we do the same thing for the other times, right? So we're going to have K2 is equal to 1 over 90 minutes. So that's going to be 1 over 90 minutes. And then we take, of course, we got to divide that, and we get, let's see, where do we get? 0.0111. 0.01111 per minute. Then we go to 0.3, that's 75 minutes. So K3 is equal to 1 over 75 minutes. Divide that, and we get 0.01333, 0.01333. And finally, we got number 4. So let's just do that over here. So K4 is going to be over 1 over 30 minutes. Okay. So we're going to have 30.0 minutes. Okay, and now that's going to be 0.03333, and that's per minute. Okay, now we have our K values. So now we need to take the natural log of those, because as I said, we need to plot the data of the 1 over the temperature versus the natural log of the K, the rate constant. So we got our rate constants. So now we just need to take the natural log of those. So let me go ahead and fix this. So give me one moment. Okay, so now I have my table set up. So here's the data that we just calculated here a moment ago for temperature, right? So we got the 1 over temperature. Here's my data. So now I just need ln of k, or the natural log of k. I have my k values here. So all I need to now do is plug these values into my calculator and take the natural log. And so I already did that. And these are the values that I got. So for point number 1, I got negative 4.905. So negative 4.9053, I believe it was. 53, yep. And that's per minute, right? So here it's going to be per minute. And then for point number 2, right? So this is 1, 2, 3, 4, right? And so for point number 2, I got negative 4.4999. So this is negative 4.4999 per minute. And then for this one, I took the natural log of that value, and I got negative 4.317, negative 4.3177 minutes, or per minutes. And then finally, I took this value here, and I got the natural log of that one. And so when I did that, I got negative 3.4012. Negative 3.4012 per minute. Okay, so again, I didn't go over the calculations in detail, but use the equations, calculate yourself, double check my work, make sure that I didn't make a mistake. I'm human. Sometimes I do make mistakes, and my viewers will point out sometimes my mistake. So double check my work, but I think I did it correctly. All right, so now you got the data here. So it says we need to graph it, right? So we need to graph the data. It says by graphing the data above. So we've now converted our data into a graphable form, so we can get our Arrhenius equation. And so I did that. So let me show you what I got here. So I went to Excel, I plotted the data, I plotted this data, and this is what I got here. It might be a little hard to read, but you can see there, that's my graph down here. This is the data that's plotted. So you can see here. And so if you do it right, you'll get an equation. You can right up here, I have the equation for the line. Y equals, I can't read it from this angle, but it's y equals something times x minus something like 1.7. That's your y-intercept form. So this is the slope-intercept form of the equation. And you can see the r-squared value. That indicates that the points fit the trend line pretty well. But the important thing is that we got this equation, and that's what we're going to use, right? So let me write down that equation there. So I'm going to go ahead and erase this, right? And so that equation that we got is y equal to negative 3068.2 times x minus 1.7603. And so that's going to be important. And so let me explain this equation to you. So when we plot our data of 1 over temperature versus the natural log of k, then what happens is this is your x value. So whenever you set up your table, right, your x values are always on this side, your y values are always on this side. So this is going to be plotted on the x-axis. This is going to be plotted on the y-axis. And when you do that, you get your Arrhenius plot, and you're going to get Arrhenius equation. So this is the point slope form, and when you put it in this form, what this is actually saying is the y values is ln of k. So we'll put in ln k here, and this we'll leave. I'll tell you that in a moment. Well, I'll tell you now. So then this is actually going to be the slope. And for the slope, when we plot this, our slope is equal to the negative of the activation energy divided by R. So this is going to be activation energy over R. And so X here, right, that's our X value. That's going to be 1 over the temperature. So we can just replace X with 1 over the temperature. And then our Y intercept, again, Y is ln of K. So then it's just going to be minus the ln of, let's see, yeah, whatever that is. So we'll say ln of k at the y-intercept when temperature is 0. Okay, so we'll put a 0 there. And so here you can have the form of the Arrhenius equation. Okay, so we have our equation. Okay, no, sorry. This is ln of a, sorry, not k, a, and that's like the pre-exponential factor in the Arrhenius equation, so that's what a comes from. So that's tied to this number here. So that's not going to be so important for our purposes, but we're asked in the first one, estimate the activation energy. Well, the activation energy is here. This is our x right here. And so that means that this number right here contains our activation energy, but this is the activation energy divided by R. So all we have to do is multiply by R. So let's take this and I'll put it over here. So here we got negative. So we have negative activation energy. So the negative of the activation energy over R is equal to this value here, which is negative 3068.2. And the unit for this is Kelvin, because why? This is 1 over temperature, so it's 1 over Kelvin. We want to cancel that out because this is going to be in terms of Kelvin as well. And so that's going to get us our activation energy, because remember, R has Kelvin in it. It also has joules per mole, so we want the Kelvin to cancel out. So there's Kelvin there along with joules and moles. So this is going to be K right? And so now that we have this, we're going to multiply both sides by R, right? So if we multiply by R here, that'll cancel out. And then we multiply by R here. But what's R? R is the gas law constant. And in this case, since we're working with joules, we're going to use the 8.314 joules per mole Kelvin form. So then that means that the activation energy here, and again, notice that this is negative and this is negative, so the negatives are going to cancel out. So the activation energy then becomes equal to 3068.2 Kelvin, right? Divided by, or I should say multiplied by 8.314 joules per mole Kelvin. Now the Kelvin cancels out and we're left with joules per mole. And so now all we have to do is multiply this by this and we'll get our activation energy in terms of joule per mole. And when we calculate that, let me go ahead and erase this to give us some room. When I calculate this, I get 25,500 and, what did I get? 509 joules per Kelvin. I'm sorry, joules per mole. And of course, typically your activation energy is in terms of kilojoules. So if we convert that to kilojoules, it's going to be, we're going to divide by 1,000 to get to kilojoules. So that's going to be 25.5 kilojoules per mole. And we're going to limit to 3 sig figs because if you notice here, all of our data is given in 3 sig figs. So that's why we have 3 sig figs here. So that would be the activation energy for the baking of chicken based on the data. Now, what about this second question? For how many minutes should you allow a similar recipe to bake if you use an oven at 400 degrees Fahrenheit? Well, now that we have the activation energy, right? Not that we really need it, but we can use that equation that we got from our graph to plug in the data. We've got the equation, so, and we've got the temperature. They're giving us the temperature. All we need to do is convert the temperature right here to Kelvin, plug that into our equation, and then we got our answer. So let's go ahead and do that. Let me write the equation back up. Okay, I am back. So I have written our activation energy. So that's the answer from the previous question. Here's the equation that I got from the graph. I replaced the little y with the natural log of k and the x with 1 over temperature. So they are giving us 400 degrees Fahrenheit. So in order to plug this into the equation, I need to convert this to Kelvin first. So using those equations I gave you at the beginning of the video, I'm going to have to convert this to Celsius first. So let's go ahead and do that in real time. So I'm going to take 400, subtract 32, equals, I'm going to multiply by 5, divide by 9, equals, and I get 204.444. So 400 degrees Fahrenheit is going to be equal to 204.444 degrees Celsius. And then to convert that to Kelvin, I'm going to add 273.15. And so let's go ahead and do that. So plus 273.15 equals, and that's 477.594 Kelvin. Okay, so now I have the temperature in Kelvin. I can plug that into this equation, and it's going to give me the natural log of the rate constant. So let's go ahead and do that. So I'm going to plug this into here. So I'm going to take the reciprocal of this temperature, right? So I'm going to take the reciprocal. So I take the reciprocal, and now I'm going to multiply that by negative 3068.2. So let's go ahead and multiply by 3068.2 equals, and then I'm going to subtract that. So I'm going to subtract 1. Let's see, 1.7603 equals, and I get, okay, so I made a mistake, but it's a minor mistake, so let me point it out. I was going to talk about this a little bit later, but I'll talk about it now. With regard to the time, you can convert this to seconds, right? You notice when I did my ln of k, I found the k constant as minutes, right? As related to the time, the reciprocal of the time. Well, I didn't change the minutes, I just kept the minutes and then did 1 over minutes and then set that equal to the rate constant. You could do the same thing with seconds, right? So a lot of times rate seconds will be in per second, or rate constants will be in per seconds. And so what you could do is you could convert minutes to seconds, take that extra step, and then plot the data in with regard to ln of k in terms of seconds, right? You don't have to do that. That's an extra step. And I did it that way as well as minutes, and I showed you the wrong graph before. Now you'll notice here, this is the original graph. Now you may not have noticed the first time, but you'll see up here that the y value there is like 1.7 something, and that's what I wrote on the board. However, that's the graph when I did it in seconds. This is the graph done in minutes. And one thing I want to point out is the slope is exactly the same, so that doesn't change anything about the slope, but our y-intercept is different. It's a positive 2 point something there, whereas before it was a negative 1.7 something. So, so the only thing we have to change here is this part here, right? So our slope stays the same, so that doesn't do anything to our activation energy, so because we use the slope to calculate the activation energy, but for the purposes of this next step, we got to make sure we have the right y-intercept. So let's go ahead and put the right one in. And that's going to be 2.334. All right, so now that when we calculate it, we'll get something reasonable. So now I'll take my temperature. I mean, it's 477.594. 594, take the reciprocal of that, multiply that by negative 3068.2, and then we're going to add 2.334 equals, and so now I have, for ln of k, I'll write it over here. So ln of k is equal to negative 4090. Negative 4090. And that's going to be, remember, that's per minutes. And so then, we know this is ln of k, so we need to get rid of the natural log. So that means we're going to take e, and then raise that to the power of the natural log of k. And then we do that to this side too, so we're going to raise that as a power of e. So that's going to be negative 4,009, or no, that should be 4.090. Sorry, forgot the point. So 4.090, and that's, oops, I shouldn't put that. I should put that. That's going to be here. So it's still, the unit is minutes or per minute. And then, of course, when you take the power, if you have natural log as a power of e, that's going to cancel out the natural log in e. So then here, k, the rate constant, is equal to whatever this is. So let's determine that. Okay, so then we have, and so now that's going to be equal to 0.0167. So k is equal to 0.0167 per minutes. Okay, so we want the time in minutes. So we're going to have to take the reciprocal of this to get minutes back. And then if we take the reciprocal of this, so take the reciprocal, and we get 59.8 minutes. So the time that it takes to cook the chicken, to bake the chicken at 400 degrees Celsius is going to be, what did I say? 59.8 minutes. 59.8 minutes. And that, ladies and gentlemen, is how you do this problem. I apologize for the mistake earlier with the y-intercept there. Again, you could do this either in minutes. They give you minutes, so you might as well just use the minutes for the time. You can convert the minutes to seconds and do it that way. It works out the exact same way. You'll get the same answer. And so I hope that helps you with this problem. I hope you enjoyed this video. If you did, if you learned anything from this video, minus the mistake, ignore the mistake. Don't judge me by my mistakes. Please go ahead and like the video. Share the video. Hit that like button somewhere around here. Also, do me a favor, subscribe to the channel. Hit that notification bell. And when you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any problems you need help with, or you need a question you need help answering, I would love to do that for you. Thanks for joining me, and have a great day.